In this task, I built an event-driven LED display using polling and software timing on the Arduino Nano 33 IoT. This system uses 6 LEDs in a straight line. It supports 2 hard-coded modes, Night Rider and Catch Me If You Can. For the hardware setup, I connect 6 LEDs in a straight line using Arduino pins D4 to D9. Each LED needs a current limiting resistor. The LED is connected to the Arduino pin through the resistor. The code is separated into 3 files. GPIO-Daemon.h defines the public interface, including the individual GPIO methods and the group display methods. GPIO-Daemon.cpp contains the direct CMSIS register operations. This is where direction set, direction clear, out set, and out clear are used. The Arduino sketch file contains the application logic. It selects the mode, pulls software timers, updates state variables, builds bitmarks, and sends the final pattern to the GPIO class. This separation makes the low-level GPIO code reusable and keeps the display behavior easier to follow. This is the header file, GPIO-Daemon.h. The first highlighted line sets GPIO group size to 6 because this task uses 6 LEDs. The next highlighted section shows the group methods. GPIO setup port X configures the 6 display pins, and GPIO display port X writes a 6-value pattern to the LEDs. The final highlighted section shows the private helper method. GetPortGroup converts a port ladder such as A into the correct SIT329 port group pointer. And the validation function checks pin numbers and binary values. This file is important because it defines the abstraction used by the rest of the project. This slide explains GPIO-Daemon.cpp, where the direct register access happens. The first highlighted block shows GetPortGroup. If the port is A, it returns port group 0. If the port is B, it returns port group 1. Inside GPIO setup port X, the code loops through the 6 display pins and builds bitmask. PMUXEN is cleared so the pins are controlled as normal GPIO rather than by an alternate peripheral. For output pins, the code adds the pins bit to output mask and writes it to direct set. For input pins, it uses direct clear and enables INEN. In the display function, the same bit masking approach is used with outset and outclear. This is efficient because selected pins can be changed without affecting unrelated pins on the port. This is the main Arduino sketch. The task requires the mode to be selected using a hard-coded variable before compilation. In the highlighted line, selected mode is currently set to mode Night Rider. To demonstrate mode 2, I change it to mode Catch Me and compile again. The timer constant defines the behavior. The polling tick is 10 milliseconds. Night Rider moves every 1000 milliseconds. In Catch Me If You Can, the left action moves every 1000 milliseconds, and the right action moves every 500 milliseconds. In loop, the program polls the selected mode and then calls delay with the polling tick. Each polling function adds 10 milliseconds to its software timer counters and checks whether a timer has expired. For the final hardware demonstration, first I will show mode 1, Night Rider. In this mode, one LED is active at a time. It moves from left to right, reverse at the end, then moves back from right to left. The movement interval is 1 second. Next, I change selected mode to mode catch me and upload again. In mode 2, catch me if you can, there are two moving LED actions. The left action moves every 1 second, while the right action moves every half second. Because the right action is faster, it looks like one light is trying to catch the other. This completes the required code explanation compile evidence in this task. Thank you.